Good afternoon, guys. How's it going? It's the 4th of March, it's a Sunday, and it's a good time to do some physics. Today I'll be answering questions 23 and 24 from the 2017 HSC Physics paper. Question 23. Using examples from special relativity, explain how theories in science are validated in different ways. Theories in science are validated by experimentation and observations. The experiments must be valid, reliable, and accurate to properly support theories. In science, the words valid, reliable, and accurate mean different things, but they lend towards the same sort of principle of supporting a theory. A valid test is a test that actually tests what it's trying, or measures what it's trying to test. Now, a silly example would be, say someone said the temperature of the day is 26 degrees Celsius, and you wanted to confirm that, and you tried to measure that using a ruler. Now that ruler doesn't give you any temperature information and gives you a completely invalid test of if it doesn't even test the temperature of the day. Now that's a silly example and no one would really do that, but there are other examples in science where that does come into play, such as the Michelson-Morley experiment, which you might know about. A reliable experiment is one which produces reproducible results. An example would be, if you wanted to test the fact the temperature is 26 degrees Celsius today, you used your thermometer this time, and you measured once that the temperature is 20 degrees Celsius. You took a second measurement and it was 30 degrees Celsius, and maybe a third measurement and it was 25 degrees Celsius. Well, those measurements have a fair bit of fluctuation between them of 5 degrees Celsius, and you would say those results are not reliable. However, if you took 3 measurements and they all recorded around very close to 26 degrees Celsius, well then you could say that's a reliable measurement of the temperature. And then finally, accurate measurements are measurements which actually allow you to measure things properly. And an example would be, if you wanted to measure the distance between Sydney and Wollongong, you'd probably measure that distance in kilometres, or even tens of kilometres. You wouldn't use a measurement like light years, because light years is the distance a light travels in a year, which is obviously very large, and it's much, much greater than the distance between Sydney and Wollongong, and wouldn't give you an accurate distance between Sydney and Wollongong. So we have to make sure our experiments are valid, reliable, and accurate to properly support theories. In the case of special relativity, time dilation has been observed in the difference between 2 atomic clocks that were calibrated before separation. One was sent on a trip around the world in an aircraft. When compared after that, the clocks were observed to be out of sync and actually recorded different times as having passed. This effect was able to be reproduced. This experiment is a valid test because it's testing the time dilation, and it properly supports the theory of special relativity. Another example of special relativity in action is our use of GPS satellites, which uses time dilation between different satellites to accurately determine position on the surface of the Earth. Now, when I was preparing this answer for this question, I looked at the question and also looked at how many marks it's worth. So it's worth 5 marks. That means it's probably going to require a bit of a good answer, or require a fair bit to the answer, I should say. So it says, explain how theories in science are validated in different ways, and using examples. So the key words there are, using examples, we have explain how theories in science are validated in different ways. So we're going to validate a test or validate a hypothesis or theory through different methods. Remember, in science, we don't really prove theories, we just support theories. We can only 100% prove a theory in mathematics. So in this example, I started by saying, here's how theories are validated using valid, reliable, and accurate experiments and observations. That's a really key part, I think. And then I backed that up with at least 2 examples. For a 5-mark question, I'm thinking I'm going to need at least 2 examples for that, maybe 3 if we're good at breaking that down. However, I'm limited for space here, and 2 examples was all I could really fit nicely. Another thing I thought about when I was trying to answer this question is I want to make it easy for the marker to read. So I make sure to use proper sentencing and proper paragraphing to make it easy to read and nice to read. A happy marker might be more lenient and give you better marks. Okay, so that's question 23. Question 24. The escape velocity from a planet is given by the formula v equals the square root of 2gm over r. The radius of Mars is 3.39 times 10 to the 6 meters, and its mass is 6.39 times 10 to the 23 kilograms. Calculate the escape velocity from the surface of Mars. Okay, so this seems like a pretty simple question. We've got r equals 3.39 times 10 to the 6 meters. We've got its mass, m, equals 6.39 times 10 to the 23 kilograms. And we've got g, the universal gravitational constant, is 6.67 times 10 to the minus 11. And that has some units that we don't need to worry about. Okay, so the question is to find the velocity. I have g, I have m, and I have r. And now I just have to plug that into the formula, and it will look like, so if I do write that in, I get v equals square root, didn't need to make it that big, but 2 times 6.67 times 10 to the minus 11 times 6.39 times 10 to the 23. If I extend that out, there we go. And that's all over 3.39 times 10 to the 6 meters. And if I plug that in my calculator, I get my velocity is, my escape velocity is equal to 5,014.5 meters per second. So important there. So the important thing there is we've got our working and we've got our unit. We've got an answer with units. It's a 2-mark question. There's probably 1 mark for the working and 1 mark for the answer with units. Units are always really important in physics or in science exams, guys. Okay. Question B. Using the law of conservation of energy, show the escape velocity of an object is independent of its mass. Okay, so the escape velocity is the velocity required for an object to escape an object's gravitational pull. In this case, a planet's gravitational pull. So planets have much more gravity than most things that we're used to. So they have a much higher escape velocity. The escape velocity of this textbook sitting near me is pretty low, in other words. Okay, to calculate the escape velocity of a planet, we have to remember that the gravitational potential, the sum of the gravitational potential energy and the kinetic energy must add to 0. Okay, so that means, well, can I leave it as that? Yeah, we'll leave it as that. So the formula for the gravitational potential energy is EP equals negative G M M over R. Is that R squared? It's just R. Okay. So the little m represents the mass of the object that's trying to escape, and the large capital M represents the mass of the planet in this case. The formula for kinetic energy of any object is equal to half mv squared. Cool. So in this case, to help us calculate the equation for an escape velocity of an object, we can just plug these 2 formulas into that first formula that we made. So we're going to substitute those 2 other formulas. So we get negative G M M over R plus half mv squared equals 0. Cool. So the thing I want to solve for here is v, because I know to get this equation for escape velocity, I need v on one side of the equation and I need everything else on the other side of the equation. So the only v in this equation is the one here. So the first thing I'm going to do is I'm going to bring this term, the term for gravitational potential energy, over to the other side of the equation. So because it's a negative on that side, I'm going to add that on both sides, or it becomes a positive when it drops the other side. So we get half mv squared equals g m m over r squared. Oh, that's not r squared, that's just r. Great. Over r. Cool. So that was the first thing to do. I had to get determine gravitational potential energy over the other side of the equation. Okay. Now, I still just need to get this V on its own. The first thing I'm going to do is I'm going to get rid of this half, and I'm going to do that by multiplying both sides by 2. So I get mv squared equals g, or 2gm m over r. I notice that it's the same m on both sides, the same little m on both sides of the equation, and because of that I can divide both sides by m, and when that happens they cancel out. So I get, I'll write it over here, v squared equals 2gm over r. And now I just need v on its own instead of v squared, so I have to take the square root of both sides. So I get the square root of v squared equals the square root of 2gm over r, and the square root of v squared is just v, so that gives us v equals the square root of 2gm. Oh, it's the wrong m. That's a very important m. 2gm over r. Cool. So we have now shown that the velocity of it, the escape velocity of an object is independent of its own mass. It's only dependent on the mass of the planet that it's trying to escape and the radius of the orbit of that planet. Okay guys, so that's been questions 23 and 24, the 2017 HSC paper. I'm trying to get better at making these videos. I'm not too experienced at it, but I am doing my best. You might notice the formats of the video are changing from video to video. Once I develop a style I like, through a bit of experimentation, I'll probably settle on that. If there's something you guys want to see, please let me know, and don't hesitate to let me know in the comment section below. So if you like this video, please like, share and subscribe, and if you dislike this video, leave a dislike and leave a comment too, just so I know and I can work on trying to improve things. Okay, thanks guys and have a good day.